I think a lot of you know about the cheetah. I certainly know about the cheetah from when I was little, because at least when I was young, it was the fastest running animal on the planet. And it's not something you typically associate with robotics. But based on not just the research, but the demos and prototypes of the next speaker, all of that may have to change. I am very, very excited to welcome Professor Sang-Bak Kim here. And we will hear about how robots, and continuing, I guess, the thread from the albatross from this morning, how robots inspired by animals is a very, very promising wave of robotic exploration. Thank you.
Thank you, Trond. Yeah. Good morning, everyone. My name is Sang-Bak Kim. I'm an associate professor of mechanical engineering right across the street at MIT. So I've been working on legged mobility for about 15 years, and I'm going to share you some idea about why we care about this technology, how it's going to be relevant to our life. Just to like step back, we last 10 years, probably maybe close to 20 years, more than 20 years, 25 years or so, we've been focusing on information. It matters a lot. Like we had a wireless technology advanced like significantly. Now everybody has this like a supercomputer in your hand, and they can do almost everything on your hand. You can do bank account, you can like send messages. We've been focusing on how to deliver the information as quick as possible using advanced even applications like Twitters. Now you can listen from president in a second or two. But the world is going to change because the information technology can be distributed very quickly because mostly software, everything is wireless. So it doesn't take much time to actually transmit your technology. When it comes to physical interaction, we saw in the manufacturing setting as well, but the physical interaction, physical service is not going to be that easy or not going to be that quickly. But it's going to come because the information delivery is oversaturating at this point. So we have to think about what kind of physical services we're going to need. Or delivery is already in the hot topic at this point. You can't deliver with those bits and atoms. You can just send a text and then deliver. You have to have some physical interaction. You have to deliver energy to the delivery. Elderly care, you start seeing this like population and demographic trend heavily in Japan and Korea, and China is better, but it's still catching up. US is also better than other countries, but the majority of the Northern Europe and the Asian countries are their population, the elderly population growth is very significant, and young population shrink very quickly. And then who is going to take care of the elderly care people? And it's the one thing big difference you can think about between the factory setting to your daily life is not repeatable. Every single time you take care of something, very simple job, you're going to have to think about very different situation. In the manufacturing setting, everything is controlled, everything is predictive. You have to fix it in repeated environment. In daily life, even like in this kind of environment, you're not going to be able to fix and then define everything perfectly. Companionship is also a problem, and like home security. You can think about many different things. The disaster response, every disaster should be different. By definition, disaster is unexpected. So I'm working on the disaster response at this point. But you have to think about many different physical services in the future. Is going to be an important part of our industry. You need mobility. You can't think about physical service without mobility. It's not a physical service. It's a booth. So you have to think about how to create this smarter mobility that we don't have at this point. Let's take a look at mobility technology just briefly. We've been conquering the entire world very effectively, very fast, actually. If you think about the history of an airplane, is only barely like 120 years. And then the ships have a much longer history. But like, I want you to kind of compare airplane, air mobility, and then water mobility on the water, or the ocean mobility, and then ground mobility. There's a big difference between air and water compared to the ground. Does anybody know what's really differentiating these two categories to the ground? You can see the difference between animals and our engineering counterpart. There are quite a bit more similarity between airplane to the birds. Maybe shark is not the right one, but they're pretty much using similar technology. When it comes to car to the cheetah, it's not even a glimpse of like similarity. I can tell you why. Because these two areas, if you look at the birds and the water mobility and the air mobility, you're constantly interact with the medium which is soft and constant. Yeah, we can talk about like a turbulence and so on, but still you're dealing with the air. Still you're dealing with water. In the ground mobility, you have to switch. Surprisingly, it took like for a long period of time, but it's surprising that switching caused so much complexity and require intelligence. What do you mean by switching? Your legs should be in the air for a while, and then you have to collide in the ground. You have to deal with that collision, which is pretty hard. Your feet is pretty compliant, but your ground is always, most likely, is very hard. And then you have to switch your controller. You have to switch all these medium change, and constantly, and sometimes very fast. The cheetah is running at, like, for example, 6 miles per hour. They're hitting about ground about 4 times in a second. So you have to deal with that transition sometimes twice. When you're walking around, you're dealing with that like twice in a second. You're not even using your forebrain to do it. You don't even know what's going on. Your body is just a know what to do. So that's why we have such a big difference between cars to the animals. Why? Because we change the environment to use our continuous technology to be valid, so you can actually change the world into the very flat terrain, so your car, continuous machine, can actually handle. How big the car has to be to handle like a curve about this big? At least you have to the SUV. I can go over about a foot height obstacle. You need a Humvee at least, or a tank to go over. My cat can probably handle those height. That's why animal evolved a certain way. We couldn't catch up with that because we actually changed the environment so that we can actually handle this mobility. We didn't do that in the air. We didn't do that in the water because you can't. You can't reshape your air to make easier technology to available. You cannot reshape your water to change, oh, this technology does not work. We did it on the ground, right? You can't have a train run without a rail. You can't have a car running without road. So now you think about it, like where are the problem we don't have of road? Stairs, curves, your toys and of your child. None of these wheeled robots would navigate in our house because their toys are everywhere. And then sometimes laundries and then the food is spilled on the floor. So we need to think about how to actually tackle this ground mobility in more general sense to do the physical interaction. So let's take a look at the manufacturing side, step back, because this is the most advanced technology we have in terms of robotics. Victor Scheinman, he just passed away about a year ago. He invented the first programmable 6-axis programmable arm, and then that became Puma and Adapt and so on. And now we are reaching a level that this robot can actually move and then do like really precision. The base is moving a lot nowadays, and then do a lot of very precise movement, very repeatably, very reliably. I cannot imagine doing this with my friend, like you tilt and then push, and then your finger can pinch in the corner. Like, human probably would be much, much worse than this. But you gotta take a look. Every factory, you go there, see if any robot actually rub or collide with the object or even the environment. What do you mean by that? Like, we do that all the time. Think about how you get out of this door, get out of this room, and then how you interact with your door. You're not approaching your door, and then now you interact, turn on, and then push. Nobody do that. You just walk through and then collide into it. But your hand is soft. You know how to handle those collisions. So you don't even think about it. How long do you think it's going to take for you to open the door, get out? It takes like less than a second. There's no single robot can do that within a minute at this point. And these manufacturing robots are fantastic in position control. They absolutely have no clue about a physical interaction and collision because it's nothing to do with the software. Your hardware, no matter what intelligence you put in, these robots cannot handle physical interaction because they're built to be very accurate and repeatable. It's very rigid. The rigidity is key to actually quality control in the manufacturing. Yet, in that kind of technology is still used in our mobility world. So you've probably seen this the robotics challenge videos. These robots are still using same kind of technology. I'm not going to show a video because it's going to make you laugh all the time, lose the point. I just trying to show that these looks like a superhero, but actually they're using same manufacturing technology. They behave very, very rigidly. And yet animals are very, very different. You don't need to even look at the YouTube video. You can play with your hand. You can play your ankles. They are constantly interacting with the environment in a very harsh way. You don't hear them because they're very quiet, and they're very efficient. Think about how accurate are they. They're not very accurate. I can't even draw a circle accurately. I can't even draw a straight line. If my hands are out of my vision, my accuracy drops down less.